Alright, grade 9s. Today we are going to look at a situation where we have a table of values and we're being asked to do something with this table of values. And understand that tables are a very interesting way and a very useful way, of course, to organize information. Not only are they nice and organized and in rows and columns and all that stuff, but they're very versatile. There are so many different ways you can look at a table and a lot of different ways to examine a table of values depending on what it is that you want to figure out from the table of values. And so there's a question that we want to answer here, and it appears in red, and it's what is the altitude when the air temperature is 5 degrees Celsius? So we're going to be trying to use this table of values in some way to answer that question. So tables, of course, are great because immediately you can at least get some idea what a reasonable answer might be. Safe to say that looking at this table, and I suppose I should introduce this table of values. It's about altitude, which is meters above sea level compared to air temperature. And to create a context for this table of values, imagine you were in a hot air balloon and you are measuring the air temperature as the hot air balloon changes in altitude. When it's 200 meters above sea level, you can see it's 26.8 degrees Celsius. Just going down to another row here, when you are 1,100 meters above sea level, the air temperature is 17.8 degrees Celsius. And then here's our question right here. What is the altitude when the air temperature is 5 degrees Celsius? Well, safe to say, looking at this table of values, because it is organized, that the answer is definitely above 2,000 meters. Now, exactly what is the answer? That's where we have to, of course, do some deeper analysis and looking at the numbers. So, and the final thing that I should say is that the air temperature changes at a constant amount compared to the altitude. So in other words, there is a linear relationship between air temperature and altitude. Okay, just want to make sure that we have that sort of all kind of in front of us. So the first thing that comes to mind when I look at a table of values like this is to try and get some sort of a picture. I'm a very visual learner, and so switching over to, instead of grid paper or something like that, switching over to Desmos can be a very useful and quick way to examine a table of values. So I'm going to insert a table here, and let's see here, table. Hopefully you can see everything on your screen there. So it was 200 meters above sea level was 26.8. 500 was 23.8. 1,000 was 18.8. 1,100 meters above sea level down to 17.8 degrees Celsius, and finally 2,000 meters, 2 kilometers above sea level, we're down to 8.8 degrees Celsius. Now as I look at my graph, of course, I don't see any dots. Where are they? Well, these numbers are so big, of course, that I have to zoom out quite a bit if I'm ever going to see these numbers. There's the first dot right there at 226.8. So I could keep on zooming out if I want and kind of slide my screen over, but I'm even going to just go ahead and click on this wrench here and change some of my minimums and maximums for my x and y. I'm going to change my minimum x to 0 so that I can see the y-axis, and my maximum, I'm going to make sure it's just a little bit over 2,000, so I'll go to 2,100. In the y direction, again, I'd like to be able to see 0 just so I can see the x-axis. Let me just go a little bit smaller so it easily shows up on my screen. And then what's my maximum need to be? Well, if I go up to 27, that'll be big enough. So just making sure this is all fitting on the screen. Okay, maybe I'll go up to 30. There we go. Okay, So if I now take a look at, let me change this a little bit here. Yeah, okay. So now as we look at this graph, we can see there's all of our dots, and there they are, making a nice linear pattern, a nice straight line pattern. If I was to try and put a line of best fit on there, I think we would see that those dots perfectly line up. Now, what we're trying to figure out is what is the altitude when the air temperature is 5 degrees. So as our very first strategy, thinking back to scatter plots and lines of best fit, we could extend this pattern and then use extrapolation and follow the 5 degrees all the way over. And we would just, slide over some more this way until we got to our answer. And that might be an okay strategy if the numbers are easy and the data is easy to look at and our scale is really easy to work with. But when it's not, that is not really that great of a strategy. And so that's where we get into things like determining the rate of change or slope that's in this relationship, and trying to determine perhaps the y-intercept, which would be when altitude is 0. In other words, you're right at sea level. And then with that equation that we might be able to write, then figure out our answer. And that's where all this is heading towards. So step 1 here is to try and figure out the rate of change or slope. So looking at the graph, things like rise and run certainly come to mind. And because these dots are making a straight line, I can use any of these 2 dots for my rise and for my run. Now that's a pretty good strategy, rise and run. We're very familiar with it. But it's a strategy that doesn't work great when the dots aren't nice, easy dots. I'm looking at these dots and they're all kind of in between these grid lines, and they're just not going to be very easy to work with at all. So as much as this graph is a great visual starting point, it's definitely not a great way to go about solving this problem. So back to the table and trying to examine these numbers some more. Well, something that certainly comes to mind when I think about a table of values is trying to figure out the first differences. Because remember, the first differences are something that can help us determine how much it's changing by vertically, right? This is the vertical column, right? This is like the X, this is like the Y, this is the vertical column, and over here is the horizontal column. So I notice that it's going down 3 degrees when this goes up 300 meters. And if over here I do a quick little calculation, slope equals the change in y divided by the change in x, which is one of our strategies or one of our ways of figuring out slope. Well, the change in y is negative 3. The change in x is 300. And changing that into a decimal, we get negative 0.01 degrees Celsius per meter. Well, what does that mean? That means that the air temperature is going down 0.01 degrees for every meter of altitude. And again, that corresponds to as we go higher and higher in our hot air balloon, the air temperature is getting lower and lower. Now we just did all that work in red, and I'm going to switch color here to maybe blue. And I'm going to go ahead and maybe try it with a different set of numbers. The reason for doing this is if you had any doubt about whether or not this is a linear relationship, you can try different pairs of numbers. So for example, this is going down 9 and this is going up 900. And just not trying to make things messy, but I'll do the calculation right here. Change in y divided by the change in x. Well, that would be negative 9 over 900. And when I convert that to a decimal, it's also negative 0.01. So the fact that these two numbers right here agree with each other and are the same certainly confirms that the rate of change is constant in this table, and they also seem to be showing a constant rate of change in the graph as well. So what I now know, and this is very useful, I'm going to go ahead and put this on the next page, is that let me change back to pen here. There we go. M equals negative 0.01. All right, that's the slope, that's the rate of change, that's how much, the temperature is changing by compared to the altitude. My next thing that I want to try and figure out from this table is, what is the y-intercept? Well, the y-intercept, don't forget, is when the line crosses the y-axis. So just looking at the Desmos graph here, somewhere up around here, right? If I just kind of visually look at it with my eyes, I can see that the y-intercept is going to be, of course, something larger than 26.8 degrees, which is this one right here, right? This is the dot 200 and 26.8 degrees. Well, the y-intercept, no doubt, is somewhere up around here, like maybe it's 28 degrees, maybe it's 29 degrees. I can't tell for sure just looking at it with my eyes, but I can definitely do some work with my table here to figure it out. So let me just copy this table. Let me see if I can do this. Give me a moment here. I really want to copy this table and bring it to a new clean slide so that all this red work and blue work isn't in the way here. I think I just did it. Let's go. All right. Let me go right here. Okay, here's our table. Let me get that out of here. Okay. So to try and figure out the y-intercept from this table, I'm essentially trying to figure out this missing number that goes in this rectangle, right? 0 meters of altitude is what air temperature? And looking at this table of values, and having looked at the first differences a little bit, we remember that it's changing 0.01 degrees for every meter of altitude. So if I could just, let's see if I can do this here. Yeah, I can insert a row. Okay, that's not where I wanted it to go. I want to see if I can put this row just below here. I want to put a whole row. Let me see if I can highlight both of these now. Not sure if I can do this the way I want to. Maybe I have to do it to both things here. Insert row, insert row. Okay, that'll work. So, 0. And I want to know, what is this? Well, looking at some of the information that I already know, again, 0.01 degrees for every meter. Well, certainly what that means, if I could work back, is that I could figure out 199 meters, and then 198, and then 197, and then 196, and yada yada yada. Oh no, that doesn't sound like a very good way. I don't want to have to create 200 more rows in my table just to work my way back to 0. I'd like to go in bigger chunks if I could. So this is where I now look at this one. I found this one's kind of interesting, because notice it goes by 100 right here. And when I go by 100, this goes down 1 degree, which makes perfect sense, right? If it goes down 1 degree for 100 meters, of course, right? -1 over 100, that certainly is consistent with that rate of change being negative 0.01 degrees Celsius per meter. Now, so counting by 100s, but I can also count backwards, right? I can figure out that 100, let me just kind of sneak it in here. Let me put in one more row. Insert row, and then over here we'll go insert row. All right. So what I know is that 100 has to be 1 degree higher. So that would be 27.8. And then finally 0 has to be 28.8. Yeah, 28.8, of course. And looking back at my Desmos graph, remember we saw this spot here, we thought, it's somewhere between 28 and 29. Well, now we know that it, for sure should have been 28.8 degrees. And that's really useful because I now know that not only is my slope, or my m value, negative 0.01, I now know that my b value is 28.8. Now, why is that great? Well, because I really want to know those two values so I can make an equation so that I can answer my question of what is the altitude when the air temperature is 5 degrees. So, my equation right now for this relationship between temperature and altitude is this, 0.01 x plus 28.8. And once I have this equation, I can definitely use it. Now, I want to figure out what's the altitude. And remember, this right here, this is the altitude. Okay, I want to figure out what is the altitude when the air temperature is 5 degrees, which is this thing right here. So, in other words, I can replace 5 for y, and I can now solve this equation for x. And here goes some of our excellent equation solving skills. Let's subtract 28 from both sides. And that gives us negative 23.8 equals negative 0.0. Hang on here. Let's go pen. Oh, I have a little glitch. There we go. Okay. And then I divide both sides by negative 0.01. And we end up getting our value for x, and our value for x is 2,380 meters. Remember, we were trying to figure out an altitude. And to figure out is that answer reasonable or not reasonable, remember what we've already been able to establish. Looking back at this table, we already knew the answer was going to be larger than 2,000 meters by some amount. Looking at the graph that we created, just to sort of give us a visual, at 5 degrees, it certainly looks like it could be somewhere between 2,200 and 2,400 meters. So when we do the math and we get 2,380 meters, that seems perfect. All of the numbers have lined up and have kind of all fit together like a jigsaw puzzle, and we can feel really confident about that answer. So what have we done here? Well, back to the table of values. Remember that this table of values contains a lot of information. It allows us to figure out rate of change. It allows us to be able to figure out the y-intercept. Okay, and sometimes we have to either work backwards or sometimes work forward in order to get that in our table. And once we have those things, we can then make an equation, which we did here, and then you can use that equation to solve for whatever it is that your question was asking. In this case, it was, what is the altitude when the air temperature is 5 degrees? All right. Now it's time for you to try. So look at today's practice questions and see how you do.